Hi everyone, my name is Nick Sultana, and I'll be telling you about the Flightplan project on behalf of my colleagues at Penn. One of the most exciting developments in networking in recent years has been its increased programmability, and in particular, the programmability of data planes. These can be implemented over a range of different devices, and most recently, the data planes of switches themselves have become programmable. One exciting development here has been that the same language can be used to program a range of different devices. A lot of research and indeed even products have been directed at developing this ecosystem. The current paradigm for data plane programming involves mapping a single data plane program to a single data plane device. While this is conceptually simple and familiar from how we program other types of hardware, it is not really well aligned with the overarching vision in software-defined networking. This is because by being forced to target a single device for a program, the software-defined network becomes hardware-confined again. We can only use the resources that individual pieces of hardware make available, rather than the collective of hardware that we have at our disposal. A much more compelling paradigm would consist of mapping our data plane program to opportunistically make use of any resources that we have in our network, and this can involve a mix of data planes. This approach would involve analyzing the resource needs of our program and then splitting it into subprograms, each of which can be mapped to hardware using the current paradigm of one program for one data plane. Let's see what this would look like in practice. I'm showing you an example here of a P4 program expressed as a flowchart. The details aren't important in this example. We have the full source code in the repository, and I will reference this example later in this presentation. The main thing I want you to take away here is what would it be like to write a distributed system from a monolith program. So we would need to start out by identifying some logic that we want to separate out from the original program. And then we would need to write the interfacing code that will hand over control between data planes, as well as hand over control back and perhaps carry out some monitoring for the purpose of diagnosis or debugging. This approach need not be restricted to offloading small pieces of logic, but could be used to offload larger subprograms as needed. Okay, so back to our original story. This new paradigm we are calling Dataplane Disaggregation, and the first part of the Flightplan paper introduces, motivates, and describes this paradigm. This is a different paradigm to server disaggregation, which we have also encountered in networking literature. Think of data plane disaggregation as programming an all-resourced virtual data plane that is then decomposed to sub-data plane programs that are mapped to physical devices. And the decomposition is aware of those resource constraints and is also aware of the objectives that we wish to meet. We also see this paradigm as helping to bridge the gap between the useful abstraction of treating the network as one big switch to a more modern rendition of treating it as one big programmable switch. Okay, so far we've seen the appeal of data plane disaggregation to make better use of the resources in our network, but how do we go about implementing it? If we were to go about implementing data plane disaggregation manually, it would be a very laborious process. There would be a lot of code refactoring to be done, and this would need to be redone every time the program changes, or if our hardware is upgraded and we need to reconsider which way to split the programming. So a good deal of automated support is needed. Let's tease out the problem a little bit more to explore this. Support is needed to analyze the program to understand its resource use, as well as to mechanically do the splitting. Moreover, we need to be able to reason about heterogeneous resources and how these can help us meet our performance objectives. Looking at the testbed we use at the university, for example, we use 3 kinds of hardware, and Each class of hardware has a different profile with regards to throughput, cost, and power, for example. The heterogeneous reasoning system needs to account for all of these, as well as perhaps more details such as latency. Since we might be using a multitude of data planes, we need to reason about placement. And since we have created a distributed system out of a monolith, we need to reason about the sort of dynamics that can arise in a distributed system, which include consistency and intermittent and distributed faults. The list doesn't stop there. The paper goes into a lot of detail analyzing the dataplane disaggregation problem. This is a new problem that the paper presents. Amongst the features that we need to abide by in order to solve this problem in a compelling way, we need to avoid language changes or hardware changes, since that would limit uptake. We also need to describe how to run multiple programs in the same network, not just one at a time. And we need to describe how debugging and diagnosis takes place in such a distributed system. The Flightplan system is a candidate solution to the dataplane disaggregation problem. It provides answers to all of the questions that we raised earlier. You can find a full system, including tests and documentation, online at the URL I have shown above. The basic idea in Flightplan is that it detours the flow of traffic in order to flow through data planes that can progressively advance the computation of the distributed program. The Flightplan process is organized into 3 phases. First, the program is disaggregated into subprograms. Second, each subprogram is mapped to hardware. And third, the individual subprograms are linked with one another in a way that is analogous to how linking works in traditional programming. The full picture is much more detailed than that, and I won't be able to expound the full details in this video. You can find those in the paper, but in this video, I'd like to give you the main takeaways. The first is that Flightplan is based on planning, which is an idea from symbolic AI that is used to explore a space. And I have reflected this idea in the name Flightplan. The second idea I want to convey is the abstractions that we use for programs and for resources, starting with programs. Here you can see a P4 source code snippet for the Crosspod program. This is the same program that earlier we saw in its flowchart form. I have highlighted 2 kinds of phrases. In orange, I have highlighted the segment annotation we use. These are used to indicate seams where the program can be split. Segments provide the maximal granularity of splitting that the program can go through. The second, in green, are resource dependencies. These are picked out automatically by the Flightplan code analyzer and converted into rules. This generation process is fully automatic. The programmer never needs to know about these rules. These rules are then fed into the planner. Just as the previous abstraction was used to reason about programs, this next abstraction is used to reason about the capabilities of different hardware. I'm showing you here 2 examples of rules that we use in our research. The paper goes into full detail about how these rules are generated and interpreted. The main takeaway here is that the formalism we're using is able to capture the capabilities of heterogeneous hardware. There's a third really interesting aspect of the system that unfortunately I can't get into in this current video. And this is the runtime system. It is a thin OS-like layer that we use to carry out fault detection and handling online in the data plane. We carried out a very rigorous evaluation of Flightplan, involving both testbed experiments and simulations. In this video, I will give you 3 salient aspects of this evaluation, and the full details can be found in the paper. Figure 10 in the paper shows the results of running an experiment in the testbed to assess the viability of distributed data plane programs. We wanted to see how activating different parts of this program could mitigate faults and also improve performance. We wanted to see that creating a distributed data plane program would be advantageous. Figure 9 in the paper shows a comparison between different plans. The different plans would make use of different hardware. The exciting takeaway from this figure is that even if we use legacy hardware, we can still get benefit from dataplane disaggregation. Figure 7 in the paper shows the results of a simulation we did that involves running multiple programs split in multiple ways using multiple runtimes in the same network simultaneously. The details of how to interpret this are in the paper, but just intuitively, what you can see there in the bottom left is a program running on the switch, and all the functions are integrated into the program. We connected this to a switch where some of the functions have been offloaded, and we progressively describe the programs running on switches in the rest of the network. All these programs are running simultaneously. To make this more accessible, we are preparing an online demo that runs in the browser that brings to life some of the static pictures that I've shown. For example, for figure 7, you're allowed to explore the topology of the network, look at the workloads, see what functions are being mapped to which part of the network, and hopefully make this accessible to a wider audience. So with that, I thank you for your attention, and I invite you to visit our website for more information.